Right now, without any effort on your part, the air in the room around you is trembling, not shaking in any way you could see if you opened your eyes and looked, not stirring the curtains or bending the light. It is trembling in a much smaller, much faster way, a flickering push and pull happening perhaps hundreds of times a second, and it is happening against your eardrums specifically, right now, whether you are paying attention to it or not. Even in what feels like silence, the air is not perfectly still. There is a hum from somewhere, a fabric rustle, the faint hiss of your own breath moving past your nose. Your body has been receiving these tiny disturbances since before you could form a memory, and it will keep receiving them tonight, tomorrow, for as long as you live, mostly without asking your permission or your attention. This is where we're going to spend some time together tonight, not with loud things, not with music or noise in the way you usually think about it, but with the actual physical event that all of that is built from, the trembling itself, what it is made of, and why it behaves the way it does. Because most people go through their whole lives hearing perfectly well without ever quite knowing what they're hearing, and there's something soothing, I think, in finally understanding a thing that has been happening to you your entire life without your noticing. So let your eyes stay closed if they already are. There is nothing to look at here. This is a listening kind of understanding, even though what we're describing is usually too fast and too small to notice as a separate sensation. You just experience the result. Tonight we walk backward from the result to the cause. Let's start with a very ordinary and slightly wrong idea, because taking it apart gently will help everything else make sense. Many people imagine that when something makes a sound, some kind of substance is being sent out from it, like a smell drifting from a kitchen, or steam rising from a cup, something you could almost picture as a stream of tiny particles heading from the source, say a bell, toward your ear, and arriving there to be sensed. It's an understandable guess. Something clearly travels. You are clearly receiving something, but nothing new is being emitted. No little packets of bell stuff, no invisible material floating across the room. What's actually happening is both simpler and, in a way, stranger than that. The air that was already there, the air that was already filling your room before the bell was struck, is the thing doing all the work. Nothing new enters the space at all. The bell doesn't add anything to the air. It disturbs it. Here's a way to picture that disturbance, without needing any technical vocabulary yet. Imagine a crowded room, people standing shoulder to shoulder, filling the space evenly, no one crammed too close together, and no one spaced too far apart. Now imagine one person near the doorway suddenly takes a half step backward into the person behind them. That person, feeling the nudge, bumps gently into the next person, who bumps the next, and a little wave of bumping travels across the room, person to person, until it reaches the far wall. Notice something important about that wave. None of the individual people crossed the room. The person by the door didn't travel to the far wall. They just moved a little, bumped their neighbor, and then mostly settled back roughly where they started. What actually crossed the room was the disturbance, the pattern of nudging, passed from person to person like a rumor passed down a line, changing hands constantly, while none of the messengers themselves went anywhere far. That, in essence, is what a sound is. Not a substance moving through the air, but a pattern moving through the air, carried by air molecules that mostly just jostle their neighbors and then return close to where they were. When a bell is struck, its metal surface flexes outward for a moment. As it does,
It pushes against the air molecules immediately touching it, crowding them closer together than they'd normally be. That crowding has a name: compression. The molecules, suddenly squeezed, push back against their neighbors a little further out, who in turn get compressed themselves, and pass that crowding onward. Meanwhile, as the bell's surface flexes back inward, it pulls away from the air right next to it, and the molecules there spread out a little more thinly than usual, into a slightly less crowded patch. That thinning also has a name: rarefaction. So what actually travels away from the bell is not the metal, not the air itself as a whole, but this alternating rhythm: crowded, thin, compression, then rarefaction, then compression again, spreading outward through the room, the way ripples spread across a still pond after a pebble breaks the surface.
The pond is actually a nice place to rest for a moment, because it clarifies something people often get backward. When a pebble drops into water and ripples spread outward in rings, the water itself is not flowing away from the point of impact toward the shore. If you've ever watched a leaf floating on a pond when ripples pass beneath it, you'll have noticed the leaf doesn't get carried toward the edge. It bobs, up, then down, then up again, staying roughly in the same spot as ring after ring passes underneath it. The ripple travels. The water, for the most part, stays. Sound in air works on that same underlying principle, just in 3 dimensions instead of 2, and with crowding and thinning of molecules instead of rising and falling of a surface. The air molecule near the bell doesn't rush across the room to reach your ear. It jostles, nudges its neighbor, and settles back. The pattern is what makes the journey. The messengers stay largely in place. It's worth sitting with why this matters, because it changes what a sound actually is at its core. A sound is not a thing, it is an event, a moving pattern of pressure, slightly higher than normal, then slightly lower than normal, then higher again, spreading through a medium like air or water or even solid material in a rhythm that repeats. Scientists sometimes describe this by saying sound is simply a pressure wave or a mechanical wave, meaning it needs some physical substance, some medium, to travel through, unlike light, which can cross the emptiness of space just fine on its own. This is why, if you were floating in the vacuum outside a spacecraft with no suit and, hypothetically, could survive it, you would hear nothing at all, no matter how close an explosion happened nearby, because there is no air out there to compress and thin out, no crowd of neighbors to pass the nudge along. Sound needs company. It needs molecules willing to jostle each other in sequence. Silence, in that sense, isn't the absence of vibration. It can simply be the absence of anything nearby for the vibration to move through. Back on Earth, of course, we are almost always surrounded by that company, by air dense enough and cooperative enough to carry these pressure patterns extremely well, which is part of why hearing feels so effortless and automatic, so unlike the deliberate act of looking at something. Your ear doesn't have to search for sound the way your eyes sometimes have to search a dark room for shapes. The compressions and rarefactions simply arrive, wave after wave, pressing gently against your eardrum in that same rhythm the bell first set into motion, faster or slower depending on what made the sound, stronger or weaker depending on how forcefully it was made. Your eardrum, in turn, becomes something like that last person in the crowded room,
receiving the final nudge in a very long chain of nudges that began somewhere else entirely, sometimes just a few feet away, sometimes, in the case of thunder, miles distant, the pattern having traveled all that way through nothing more solid than moving, jostling air. It's a strange thing to realize that hearing your own name spoken across a room involves no actual piece of that name traveling to you. No little fragment of the speaker's breath makes the journey intact. What makes the journey is a pattern, compression following rarefaction following compression, shaped a particular way, that began as a vibration in someone's throat, or a page turning, or a bell struck metal, and simply passed itself along, molecule to molecule, message to message, until it reached you and became, for just a moment, something you could feel and then understand.
Once you can picture that plainly, the crowded room, the pond ripple, the passed-along nudge, a great deal of what seems mysterious about sound starts to loosen and make sense. And once that groundwork is settled, we can start looking more closely at the shape of these traveling patterns themselves, at what makes one wave feel different from another, and why some disturbances reach you as a deep, slow rumble, while others arrive as something impossibly high and thin. Let's follow one of these traveling patterns all the way to its destination, because the journey doesn't end at the eardrum, not by a long way. That thin membrane is really just the beginning of a much longer relay, one that turns air pressure into something else entirely before your brain ever gets involved. It helps to slow down here, to walk through it almost frame by frame, the way you might watch something happen in very still water. The outer ear, that curled shape of cartilage on the side of your head, isn't just decoration. It's a kind of funnel, gathering pressure waves from a wide area and guiding them inward, down a short curved tunnel called the ear canal. The shape matters more than people usually assume. Its folds and ridges subtly shape incoming sound before it even reaches the eardrum, helping your brain later guess whether something came from above or below, from in front or behind. You've likely done this without noticing, tilting your head slightly toward an unexpected sound, letting your outer ear do a small, automatic job of triangulation. The canal itself narrows and curves just enough to protect what lies at its end, while still funneling sound efficiently inward, the way a narrow hallway can carry a voice further than an open field would. At the end of that canal waits the eardrum, properly called the tympanic membrane, a taut, cone-shaped sheet of tissue barely a third of a millimeter thick. It's easy to picture it as fragile, and in some ways it is, but it's also remarkably responsive, capable of moving in response to pressure changes so small they'd be almost impossible to measure by any means other than hearing itself. When a pressure wave arrives, compression pushes the eardrum inward just slightly, and the following rarefaction lets it spring back out, over and over, matching the rhythm of the wave that reached it. A deep, slow sound moves the eardrum in a slow, wide sway. A high, thin sound moves it in a fast, small flutter. The eardrum doesn't know or care what made the sound. It simply moves the way the air moving against it tells it to move, faithfully, without interpretation, the way a flag doesn't choose how it flaps, but only follows the wind pressing against it. What happens next is where hearing starts to feel almost like a piece of clever old machinery, because on the other side of that eardrum sit 3 tiny bones, the smallest bones in the entire human body, linked together,
like a miniature drawbridge mechanism. They're named, rather charmingly, for the shapes early anatomists thought they resembled: the malleus, meaning hammer, the incus, meaning anvil, and the stapes, meaning stirrup, that last one small enough to rest on a fingernail, with room to spare. These three ossicles, as they're collectively called, form a connected chain: the malleus, attached directly to the inner surface of the eardrum, the stapes pressing, at the far end, against a much smaller membrane, called the oval window, which forms the entrance to the cochlea itself. The purpose of these three little bones isn't simply to pass vibration along, though that's part of it. Their real job is to solve a physical problem that would otherwise cause most sound to be wasted before it ever reached the inner ear. The eardrum vibrates in air, but the cochlea beyond it is filled with fluid, and fluid resists movement far more than air does, the same way pushing your hand through water takes more effort than pushing it through open air. If the eardrum tried to shake that fluid directly, most of the vibration would simply bounce back, lost, the way a shout, aimed at a swimming pool, mostly reflects off the surface rather than disturbing the water below. The ossicles solve this by acting as a kind of mechanical lever system, concentrating the force from the wide eardrum down onto the much smaller oval window, and in doing so, they amplify the pressure enough to actually push those vibrations into fluid, rather than have them wasted against it. It's not unlike using a small hammer with a long handle to drive a nail with far less effort than pressing directly with your thumb, the mechanics rearranging force so that a gentle push becomes an effective one. By the time a vibration reaches the stapes and presses against the oval window, it has traveled quite a strange path already, air pressure becoming membrane movement, becoming a chain of tiny bones rocking in sequence. And yet none of this, not the outer ear, not the eardrum, not the hammer, anvil, or stirrup, has produced anything resembling what we'd call hearing. It's still just motion, still just physics, working out force and resistance, patient and mechanical, the way gears turn in a clock, without the clock knowing what time it is. The real transformation happens next, inside the cochlea, a spiral structure about the size of a pea, coiled like a small snail shell, which is in fact where its name comes from, the Latin word for snail. Inside that coiled shell lies fluid, and running through the fluid is a delicate structure called the basilar membrane, which stretches the length of the coil, narrow and stiff near the entrance, wider and floppier near the tip. When the stapes pushes against the oval window, it sends a ripple through the cochlear fluid, and this ripple causes different parts of the basilar membrane to bend and flex in response, but not evenly along its whole length. High-frequency vibrations cause the most movement near the stiff, narrow base of the membrane, while low-frequency vibrations cause the most movement near the wider, floppier tip, a natural sorting of pitch by physical location, something like a piano keyboard, laid out inside your head, low notes at one end, high notes at the other, arranged not by choice but by the simple physics of stiffness and width. Resting along this membrane are the true marvels of the entire system, tiny structures called hair cells, though the word hair here refers to their appearance rather than anything soft or delicate. Each hair cell has a small bundle of stiff projections on top, called stereocilia, arranged like a tightly grouped set of reeds. When the basilar membrane bends beneath them, these stereocilia tilt, and that tilting opens tiny channels in the hair cell, letting charged particles flow in, and that flow generates an electrical signal. This is the actual moment vibration, stops being purely mechanical, and becomes something a nervous system can use, a translation point as significant as the one where light striking your retina becomes an electrical message, rather than simply illumination. It happens quietly, constantly, without any sensation of effort, thousands of these hair cells tilting in patterns that mirror the shape of the sound that arrived, each one reporting a tiny piece of the larger picture. These electrical signals gather at the base of each hair cell and pass into fibers of the auditory nerve, which bundles tens of thousands of these individual threads together into a single thick cable, leading out of the cochlea and into the brainstem. It's worth pausing on this, because it means that everything you've ever heard, every voice, every song, every creak of a house settling at night, arrived at your brain not as sound at all, but as patterns of electrical pulses traveling along nerve fibers, no different in basic nature from the electrical signals carrying information anywhere else in your body. The rumble of thunder and the ring of a bell are, by the time they reach your brainstem, simply different patterns of firing, different rhythms and combinations among those thousands of nerve fibers, distinguished only by which fibers fired, how often, and in what sequence. And this is really the heart of the strange truth sitting underneath all of this machinery. Nothing about the cochlea, the ossicles, or the auditory nerve actually produces the experience of sound. What they do, remarkably well, is convert one kind of pattern into another, air pressure into membrane movement into fluid ripple into electrical pulse. The transformation from electrical pulse into the felt experience of hearing, the warmth of a familiar voice, the comfort of rain against a window, happens somewhere further along, deep inside the brain itself, in ways that are still only partly understood, even now. Before we go there though, it's worth spending a little more time with the wave itself, because the shape of that original pressure pattern, how tightly packed its compressions are, how tall its pushes and pulls, carries information your ear has been quietly decoding this whole time.
So let's slow down and look at the wave itself, the thing that started this whole journey before it ever touched an eardrum. A sound wave, at its core, is just air pressure rising and falling, pushing molecules closer together and then letting them spread apart again, over and over, many times each second. And two of the simplest questions you can ask about that pattern turn out to explain most of what we mean when we talk about how a sound feels to hear. The first question is how fast the pushing and pulling repeats. If you could watch the air molecules near a tuning fork, you'd see them bunch together, spread apart, bunch together again, in a steady rhythm, and the number of times that full cycle happens in 1 second is called the frequency. A slow rhythm, maybe 50 or 60 repetitions each second, gives you a low rumble, something like the hum of a refrigerator settling into its work for the night. A fast rhythm, many thousands of repetitions each second, gives you a high, thin sound, something like the whine of a mosquito circling in the dark. Frequency is measured in a unit called Hertz, named after Heinrich Hertz, the German physicist who in the late 1880s proved that electromagnetic waves existed at all by generating and detecting them in his laboratory, work that had nothing directly to do with sound, but gave us the word we now use to count wave repetitions of every kind. 1 Hertz simply means 1 complete cycle per second. Now here's where it gets interesting, because frequency is a physical measurement, something you could capture with an instrument even if no living creature were around to hear it. Pitch, on the other hand, is what your brain constructs when it receives information about frequency. Pitch is the felt sense of a sound being high or low, the reason a cello sounds low and a piccolo sounds high, and for the most part, pitch tracks frequency quite faithfully. Double the frequency, and you get a sound that feels like it has jumped up by what musicians call an octave.
a relationship so old and so universal across human cultures that it likely reflects something built into the structure of hearing itself, rather than a taste picked up through habit. But pitch is not identical to frequency, and the two can come apart in curious ways. Play a very quiet tone and a very loud tone at the exact same frequency, and many listeners will report that the loud one sounds very slightly lower in pitch, even though nothing about its frequency changed at all. Your brain is not simply reading off a number, it's making a judgment, and judgments can be nudged by things that seem, on paper, unrelated. The second basic question you can ask about a sound wave is how big the pushing and pulling is, not how often it happens, but how forceful each push is. This is amplitude, and you can picture it by imagining someone pushing a swing. Frequency would be how many times per minute they push, while amplitude would be how hard each push is. A gentle push and a forceful push might happen at exactly the same rhythm, but the swing will travel much higher and faster with the forceful push. In a sound wave, amplitude corresponds to how tightly the air molecules bunch together during each compression, which in turn is what our ears experience as loudness. And just as with pitch and frequency, loudness is not a simple, direct readout of amplitude. Loudness is the brain's constructed impression of how intense a sound seems, and it depends on frequency as much as it depends on amplitude itself. This is one of those facts about hearing that feels almost unfair once you learn it, because it means two sounds can carry the exact same physical energy and still seem wildly different in how loud they are. A deep bass tone and a mid-range tone, matched perfectly in amplitude, will not sound equally loud to a typical human ear. The mid-range tone, somewhere around 2,000 to 5,000 Hz, will usually sound considerably louder, because that is roughly the frequency range where human hearing is most sensitive, likely shaped by the acoustics of the ear canal itself, which naturally amplifies frequencies in that region, along with the frequency range most useful for understanding speech.
This unevenness across the frequency spectrum was mapped out in careful listening experiments in the early 20th century, most famously by the researchers Harvey Fletcher and Wildon Munson working at Bell Labs in the 1930s, who asked volunteers to judge when tones of different frequencies sounded equally loud, and from those judgments built curves showing just how much extra amplitude a very low or very high tone needs before it feels as loud as a mid-range one. Those curves still bear their names today, the Fletcher-Munson curves, and they explain something you may have noticed without ever putting words to it, that turning the volume down on a stereo late at night seems to drain the bass out of the music long before the vocals fade, because at lower overall volumes, your ear's uneven sensitivity across frequencies becomes more pronounced, and the low end simply falls below what your ear can easily register, while the mid-range voices remain clear. There is a third measurement tucked into the shape of a wave, closely related to frequency but describing something slightly different, and that is wavelength. If frequency tells you how many times per second the pattern repeats, wavelength tells you the physical distance the wave travels during one complete cycle, essentially, how much space one full push and pull takes up as it moves through the air. Picture ripples spreading across a still pond after a stone drops in. The ripples that are close together, tightly packed, correspond to a high frequency and a short wavelength. The ripples that are spread far apart correspond to a low frequency and a long wavelength. The ripples, wavelength. So sound behaves the same way, and because sound travels through room temperature air at a fairly constant speed, somewhere around 340 meters per second, frequency and wavelength
are locked together in a simple relationship. When one goes up, the other comes down. This is part of why very low sounds, like the rumble from a passing truck, seem to move through walls and around corners so easily. Their wavelengths can stretch to many meters long, sometimes longer than the wall itself, which makes it much harder for the wave to be blocked or absorbed the way a short, tightly packed high-frequency wave can be. Alongside frequency, amplitude, and wavelength sits a quieter, more subtle property called phase, which describes where in its cycle a wave happens to be at a given moment, whether it's in the middle of compressing, in the middle of spreading apart, or somewhere in between. Phase becomes important the moment more than one wave is present at the same time, because waves can align with each other, called being in phase, in which case their pushes and pulls reinforce one another, and the resulting sound grows stronger. Or they can fall out of step, called being out of phase, in which case one wave's push happens to land at the same moment as another wave's pull, and the two can partly or even fully cancel each other out. This is not a rare curiosity confined to physics demonstrations. It's the exact principle behind noise-canceling headphones, which listen to the incoming sound around you and generate a new wave, carefully timed to be almost perfectly out of phase with it, so that the two waves largely erase each other before they ever reach your eardrum.
So far, everything we've described, frequency, amplitude, wavelength, phase, could in principle be captured by a single pure tone, one smooth, simple repeating wave with nothing else going on. But almost nothing you hear in ordinary life is actually that simple. A note played on a violin and the very same note played on a piano can share an identical frequency and an identical amplitude, and yet no one would ever mistake one instrument for the other. What separates them is called timbre, sometimes described, a little unhelpfully, as tone color, and it exists because real instruments, real voices, and real everyday sounds almost never produce just one pure frequency at a time. Instead, they produce a fundamental frequency, the one that mostly determines the pitch you perceive, layered together with a whole family of quieter additional frequencies called overtones, riding along above it, and it is the particular blend of which overtones are present, and how loud each one is relative to the others, that gives every voice and every instrument its own distinctive fingerprint, an idea worth sitting with a little longer, because it turns out the shape of that blend is not fixed at all, but shifts and breathes as a sound unfolds over time. Let's slow down for a moment and just sit with something simple, something you've probably felt without ever quite naming it. Sound needs something to travel through. It needs a medium, a substance whose particles can bump into each other and pass the disturbance along, and depending on what that substance is, sound moves at wildly different speeds. This is worth understanding gently, because it explains a lot of small mysteries you've probably noticed and never chased down. In ordinary air, at a comfortable room temperature, sound travels at around 343 meters per second. That's roughly 767 miles per hour. Fast, certainly, but not instant. Sound in air is really just a chain reaction of air molecules jostling their neighbors. One molecule gets pushed, it pushes the next one, that one pushes the next, and so on. A relay race happening trillions of times a second. And here's the thing about a relay race. Its speed depends entirely on how close together the runners are standing and how energetically they're moving. Now imagine, Instead of air, you're dealing with water. Water molecules are packed far more tightly than air molecules. There's barely any space between them. And because they're already so close together, a disturbance doesn't have to travel far before it bumps into the next molecule and gets passed along. Sound moves through water at around 1,480 meters per second, more than 4 times faster than in air. This is actually why, if you've ever been swimming and put your head under water while someone tapped on the pool's edge, or knocked 2 rocks together beneath the surface, the sound arrived feeling strangely sharp and strangely close, almost as if it had no distance to travel at all. In a real sense, it didn't have as far to travel, not in terms of empty space between particles. Push this even further, into a solid, say a steel rail or a length of iron pipe, and the molecules are packed tighter still, locked into a rigid structure, practically touching. Sound through steel travels at around 5,900 meters per second, nearly 15 times faster than through air. There's an old story, repeated in many forms, of engineers and railway workers in the 19th century pressing an ear to a train track to detect an approaching train long before it could be seen or heard through the air. Whether every version of that story is precisely accurate hardly matters, because the physics behind it is entirely real. The vibrations from a distant train reach a listener's ear far sooner through solid metal than they ever could drifting through open air, simply because the atoms in steel are so close together and so stiffly connected that each one barely has to move before it sets its neighbor moving too. So here's a small rule worth letting settle in your mind before we go further. Broadly speaking, sound travels fastest through solids, slower through liquids, and slowest through gases. It is, in a strange and almost poetic way, exactly backwards from what your intuition might expect. We tend to think of solids as things that don't move, dense, heavy, immovable objects, and we think of air as light, thin, easy for anything to pass through. But sound isn't a solid object slipping past obstacles. Sound is a message, passed hand to hand, and it's the closeness of those hands, not their weight, that determines how quickly the message travels. There's a second variable tangled up in all of this, and it's temperature, and it applies especially noticeably to sound moving through air. Warmer air makes sound travel a little faster, and cooler air makes it travel a little slower. The reason comes back, again, to those jostling molecules. In warmer air, the molecules already have more energy. They're moving faster and colliding more often and more forcefully, purely because heat is, at the molecular level, just motion. So when a sound wave arrives and needs those molecules to pass along a disturbance, warm, energetic molecules do it a bit more readily than cold, sluggish ones. The difference isn't enormous around everyday temperatures, but it is measurable and real, and it has genuine consequences. Musicians who play wind instruments, and to some extent brass instruments, actually contend with this quite directly. A flute or a clarinet produces its pitch based partly on the speed of sound inside the air column of the instrument itself, and because that speed shifts with temperature, an instrument that was tuned perfectly in a cool rehearsal room can drift slightly sharp once it warms up under stage lighting, or once a musician's own breath, which is considerably warmer than room air, has been filling the instrument for the better part of an hour. Orchestras have long known, informally, that a concert hall's temperature isn't just a comfort question. It can nudge an entire ensemble slightly out of tune with itself, one instrument warming faster than another. It's a small, quiet detail, easy to miss, but it's been shaping how musicians warm up and tune their instruments for centuries.
Temperature differences in open outdoor air can do something even stranger, something that explains a phenomenon many people have noticed on a still evening without ever knowing why it happens. Sound seems to travel unusually far across water or across an open field, right around dusk. Part of this is simply that the world tends to grow quieter at that hour, less background noise to compete with. But part of it is genuinely about temperature layering. In the evening, the ground and the air just above it cool faster than the air higher up, so you end up with a layer of cooler air near the surface and warmer air above it, the reverse of the usual daytime pattern.
Sound waves bend, ever so slightly, toward regions where they travel more slowly, and this bending, this gentle curving of the sound's path back down toward the cooler layer near the ground, can trap sound close to the surface and carry it much farther than it would travel on a warm afternoon when the usual temperature pattern lets sound simply drift upward and disperse into the open sky. So if a conversation from across a lake once reached you with startling, almost eerie clarity on a calm evening, that wasn't your imagination, and it wasn't magic. That was air temperature quietly bending sound's path for you. Now, echoes. An echo happens because sound doesn't only travel in a straight line toward a listener, it also spreads outward from its source in every direction it can, and some of that spreading sound strikes a distant hard surface, a canyon wall, a large building, the far side of a stone hallway, and bounces back. What makes an echo distinct from ordinary reverberation, the kind of soft, blurry decay you hear talking in a small tiled bathroom, is timing. If a reflected sound arrives back at your ear within roughly a tenth of a second of the original, your brain simply fuses the two together. It interprets them as one continuous sound rather than two separate events, and that's what reverberation is. That's the pleasant, thickened quality of sound in a stone cathedral. But if the reflected sound takes longer than about a tenth of a second to return, longer because it had farther to travel, your brain hears it as a genuinely separate, distinct repetition. That's an echo. And because sound travels at that fairly fixed speed of around 343 meters per second in air, you can actually work out roughly how far away a reflecting surface is just by timing the delay. A 1-second gap between a shout and its echo means the sound traveled there and back in that 1 second, roughly 170 meters each way. People have used exactly this kind of reasoning long before anyone had modern instruments to estimate distances across canyons and valleys simply by shouting and counting. Which brings us, gently, to somewhere sound cannot go at all. Space. Ordinary outer space, the vacuum stretching between planets and stars, is silent, genuinely and completely silent, and this often surprises people who grew up watching films where spaceships roar past each other and explosions thunder in the void. But remember what sound actually is. It's a mechanical vibration, molecules jostling their neighbors, one after another, in an unbroken chain. Take away the molecules, and there is nothing left to jostle, nothing to pass the vibration along. A vacuum has, by definition, essentially no matter in it, no air, no water, no solid medium of any kind, so a sound wave produced there has no relay of neighboring molecules to travel through, and it simply cannot exist as sound at all. If you could somehow survive, unprotected, in the vacuum near a genuinely enormous explosion, you would see it. Brilliant light travels through a vacuum without any trouble, since light isn't a mechanical vibration of matter the way sound is, but you would never hear the blast, not from any distance, not even from very close. There would only be a vast, absolute,
and rather uncanny silence, and it's this silence that raises a curious follow-up question, worth turning to slowly.
Let's leave that silence behind for a moment and turn toward something almost opposite. The way certain objects seem to come alive with sound, seemingly on their own, simply because the right note passed by. This is resonance, and once you notice it, you start hearing it everywhere. Every object that can vibrate has what's called a natural frequency, sometimes several of them at once. Think of a playground swing. Push it at random moments, and you fight against its motion, wasting effort, barely getting it moving. But push it at the right moment, in rhythm with its own back and forth motion, and each small push adds to the last. The swing climbs higher with what feels like very little effort from you. That rhythm the swing prefers, that particular timing it seems to want, is its natural frequency, the pace at which it can store and release energy most efficiently. Almost everything around you has one, or several, a wine glass, a bridge, a guitar string, a column of air inside a bottle, even a room itself. It's simply a property of the object's shape, size, stiffness, and mass, the specific pace at which it likes to oscillate if left undisturbed. Resonance happens when an outside vibration arrives at that same natural frequency, and the object responds by vibrating with far greater amplitude than the outside force alone would seem to justify. It's the sound version of that swing, being pushed at exactly the right instant, and the classic demonstration, the one people love to bring up, involves an opera singer and a wine glass. This isn't a myth, though it's often told with more drama than it deserves. Every wine glass has a natural frequency. You can find it yourself quite easily. Just wet a fingertip and run it slowly around the rim, and the glass will sing back a clear, sustained tone. That tone tells you the glass's natural frequency. If a singer can produce that exact pitch, loudly and steadily enough, and sustain it long enough, the sound waves pumping against the glass, again and again, in time with its own natural rhythm, can build the glass's vibration up and up, like repeated pushes on that swing, until the glass is flexing more than its structure can bear, and it shatters. It requires precision, sustained volume, and often a particularly thin, resonant glass, which is why it's rare and impressive rather than easy. But the physics behind it is entirely ordinary. No mysticism required, just push, at the right moment, over and over. Bridges have their own natural frequencies too, and this has occasionally mattered in more serious ways. Soldiers marching in step across old bridges have, historically, sometimes been ordered to break stride, to walk out of rhythm rather than in it, because a large group of feet landing together, again and again, at a steady pace, can accidentally act like that repeated, well-timed push, especially if their marching rhythm happens to land near the bridge's own natural frequency. The bridge can begin swaying more than intended, not because marching feet are especially powerful, but because the timing lines up, and small pushes accumulate. The most famous cautionary tale involving resonance and a bridge is a bit more complicated in the retelling than people often assume. The Tacoma Narrows Bridge, which collapsed dramatically in 1940, is frequently described as simple wind-driven resonance, but the fuller explanation involves a related, but somewhat different phenomenon, called aeroelastic flutter, where wind flowing across the bridge deck created a feedback loop between airflow and the structure's twisting motion. It's a cousin of resonance, related in spirit, worth knowing the nuance exists, rather than repeating the simplified version as if it were the whole story. Now, back to something gentler, and closer to your own body, your voice.
When you speak or sing, your vocal cords vibrate, but that alone would produce a fairly thin, buzzy sound, nothing like the rich voice you actually hear. The warmth and character of a human voice comes largely from resonance, specifically from the shape of your throat, mouth, and nasal passages, which act as a resonating chamber, the same basic principle as that column of air inside a wine bottle or an organ pipe. As the buzzy sound from your vocal cords travels upward through your throat and mouth, certain frequencies within that raw sound get reinforced, amplified by resonance, while others fade, simply because of the specific size and shape of the cavity the sound is passing through. Change the shape of that cavity, just slightly, by moving your tongue, your jaw, your lips, and you change which frequencies resonate, which is largely how you form different vowel sounds. Say ah, and then slowly shift toward e, and notice how much is happening just with the shape of the space inside your mouth, reshaping which frequencies get favored, moment to moment. This same idea of certain frequencies being favored and reinforced connects directly to something called harmonics, and it's worth sitting with slowly, because it explains why a violin and a trumpet playing the exact same note still sound utterly different from one another.
When you pluck a guitar string, or blow across the top of a bottle, or buzz your lips into a trumpet mouthpiece, you rarely produce just one clean, pure frequency. Instead, the vibrating string or column of air moves in several patterns simultaneously, layered on top of each other. There's the fundamental frequency, the lowest, simplest pattern, the one that mostly determines what note you perceive yourself to be hearing. But riding along with it are additional patterns, called overtones or harmonics, vibrating at whole number multiples of that fundamental frequency, twice as fast, 3 times as fast, 4 times as fast, and so on, each one quieter than the last, each one blending together with the fundamental into a single perceived sound. The particular mixture of these overtones, which ones are louder, which ones are barely present, is called timbre, and it's essentially the fingerprint of a sound. A violin string and a trumpet's air column can both be tuned to vibrate at the same fundamental frequency, producing what we'd call the same musical note, the same pitch, and yet their overtone patterns differ enormously because of differences in material, shape, and how the vibration gets started in the first place, bowing versus buzzing lips against a mouthpiece. Your ear and brain, remarkably, blend all those overtones together into one unified sound, yet still somehow extract enough distinguishing information from that blend to instantly recognize a violin as a violin and a trumpet as unmistakably not a violin, even at the same pitch, even at the same volume. It's a bit like how two people can say the exact same word at the exact same pitch and loudness, and you can still usually tell their voices apart because the fine texture, the particular blend of resonant frequencies each voice produces, differs from person to person, shaped by the individual size and shape of their throat and mouth. There's a related, quieter phenomenon worth mentioning here too, called sympathetic vibration, closely related to resonance, but distinct enough to deserve its own name. If you've ever pressed down the sustain pedal on a piano, without striking any key at all, and then sung or shouted a note loudly nearby, you may have noticed certain piano strings beginning to hum softly on their own, seemingly without anyone touching them. What's happening is that with the pedal down, the dampers lift off every string, freeing them to vibrate. Sound waves from your voice, traveling through the air, reach those free strings, and while most strings simply ignore a frequency that doesn't match their own natural frequency, any string whose natural frequency happens to correspond to a frequency present in your voice, whether as your voice's fundamental or one of its own overtones, will begin to vibrate along with it, quietly, sympathetically, borrowing energy from the sound in the air. Indian classical instruments like the sitar are built deliberately around this same idea, with a whole separate set of sympathetic strings that are never plucked directly by the player at all, and simply exist to resonate quietly whenever the main strings above them produce a matching frequency, adding a subtle, shimmering layer underneath the primary notes. Rooms themselves have natural frequencies too, something acousticians spend careers thinking carefully about, particularly in spaces built for music, where certain sizes and proportions of a room will naturally reinforce specific frequencies more than others, creating what are sometimes called room modes, spots where certain bass notes seem to swell unexpectedly or fade out almost entirely, purely because of where the standing wave pattern happens to reinforce or cancel itself within that particular space. And that phrase, standing wave, deserves some slow, unhurried attention of its own, because it's really the underlying mechanism behind almost everything resonance-related that we've just wandered through together, and it's where we'll turn next. Let's leave rooms and their standing waves resting quietly for a moment, and turn instead towards something you've been doing so effortlessly your whole life that you've probably never stopped to marvel at it, which is figuring out where a sound is coming from without ever looking. Close your eyes right now, if you like, and just listen. Somewhere, maybe, there's a hum of traffic, or a fan, or the particular silence of a quiet room, which is never really silence at all, and without any effort, without any conscious calculation, you have a sense of where these sounds live in space around you. This one is off to your left. That one is behind you and slightly above. This is such an ordinary experience that it barely registers as an achievement, and yet it depends on a set of calculations so precise and so fast that engineers who try to replicate them in machines still find themselves humbled by the problem. The story begins with the simple fact that you have two ears, one on each side of your head, separated by a small but meaningful distance, usually somewhere around 20 centimeters if you measure the path sound has to travel around the curve of your skull. That gap is the whole foundation of spatial hearing. Because your ears are not in the same place, a sound arriving from one side reaches the near ear first and the far ear a fraction of a moment later. This is called an interaural time difference, and the delays involved are almost unimaginably small, often less than a single millisecond, and yet your brain has evolved circuits specifically devoted to detecting differences of even a few dozen microseconds between the two ears. There are neurons deep in the brainstem, in a structure called the medial superior olive, whose entire job, as far as anyone has been able to determine, is to compare the timing of signals arriving from the left ear and the right ear, and to fire most strongly when that timing difference matches a particular angle. It's a kind of biological stopwatch, tuned not to seconds but to fractions of a millisecond, and it was actually a physiologist named Lord Rayleigh, back in the late 19th century, who first worked out in careful detail that timing differences like these could explain how we localize low-frequency sounds. But timing alone doesn't tell the whole story, and Rayleigh noticed this too. For very high-frequency sounds, the wavelengths involved become so short that timing differences between the ears grow ambiguous, because the wave cycles so quickly that the brain can no longer reliably tell which peak arrived first. So for higher-pitched sounds, your hearing system leans on a different cue instead, something called an interaural level difference. This one is simpler to picture. Your head itself is a physical obstacle, a rounded mass of bone and tissue sitting between your two ears, and for high-frequency sound,
which doesn't bend easily around large objects, your head casts something like an acoustic shadow. A high sound coming from your right will strike your right ear at close to full loudness, while your left ear, shielded behind the curve of your skull, receives a slightly quieter version. Your brain compares these two loudness levels, much the way it compares timing, and uses the difference to estimate direction. Together, these two systems, timing differences for low sounds and loudness differences for high sounds, form what's often called the duplex theory of hearing, first laid out clearly by Rayleigh himself, and it remains, more than a century later, a remarkably good description of how horizontal sound localization actually works.
Now, if you're picturing this so far, you might already sense a problem lurking underneath it. Timing and loudness differences can tell your brain quite a lot about whether a sound is coming from your left or your right, but they run into trouble when it comes to distinguishing front from back, or above from below. Imagine a sound source positioned directly in front of your nose, and then imagine that same sound source move to a position directly behind the back of your head. In both cases, the sound reaches your two ears at exactly the same time and at exactly the same loudness, because the geometry is essentially mirrored. And it isn't just those 2 points. Picture an entire imaginary cone extending outward from each ear, its surface made up of every point in space that produces that same identical timing and level difference. Acousticians actually call this the cone of confusion, and it's a wonderfully honest piece of technical vocabulary because confusion is exactly what happens when a sound source sits somewhere along that curved surface. Timing and loudness cues alone simply cannot distinguish those positions from one another. So how do we usually manage to tell the difference anyway, most of the time, without even noticing there was a puzzle to solve? Part of the answer lies in the strange, individual, almost fingerprint-like shape of your outer ear, the visible folds and ridges of cartilage that most of us barely think about except when we're wearing glasses or earrings. That curling structure, called the pinna, isn't just decorative, and it isn't simply a funnel for gathering sound either. Its folds and cavities reflect and delay sound waves in extremely subtle ways before they reach the eardrum, and crucially, they do this differently depending on whether the sound is arriving from above or below, from the front or from behind. These tiny reflections alter the balance of frequencies in the sound ever so slightly, boosting some frequencies a little and canceling others, creating a kind of acoustic signature that changes with the angle of arrival. Researchers call this a spectral cue, and it's genuinely learned rather than simply hardwired, which is part of why localizing sound directly in front versus directly behind or overhead tends to feel just slightly less certain than localizing left from right. Your brain has spent years quietly learning the particular filtering signature of your own particular ears, and that learning is personal enough that if you listen to a recording made using someone else's ear shape captured through tiny microphones, the spatial illusion often doesn't work quite as well for you as it would for them. There's one more trick available to a listener that none of this timing, or level, or spectral analysis alone can offer, and it's simply this: you can move your head. If a sound's position is ambiguous, sitting somewhere on that cone of confusion, a small tilt or turn of the head changes the geometry entirely, shifting the timing and level differences in a way that resolves the ambiguity almost instantly, without you ever consciously deciding to test anything. Owls, incidentally,
Take this principle to an extraordinary extreme, with facial discs that funnel sound asymmetrically into two ear openings positioned at slightly different heights on either side of the head, giving them precise vertical as well as horizontal localization, useful when you're hunting mice under snow using hearing alone, which barn owls have been shown capable of doing with real precision. And then there's one final layer to how we sense space through sound, something less about pinpointing a single source and more about sensing the room itself, and that's reverberation. When a sound is produced in an enclosed space, some of it travels directly to your ears, but much more of it bounces first, off walls, off ceilings, off furniture, arriving a little later and from many different directions at once, blended together into a soft trailing wash. Your brain uses the balance between that direct sound and all that later reflected sound as a cue for distance, so that a sound with relatively more direct energy compared to reverberant energy seems close, while one drowned in reflection seems far away, even at the exact same loudness. This is part of why a good recording engineer, working carefully with reverb and delay in a mix, can convince your ears that a voice is standing right beside you in an intimate room, or shouting from far across a cavernous cathedral, using nothing more than two small speakers or a pair of headphones sitting a few centimeters from your skull. It's an illusion built entirely out of these same cues: timing, level, spectral shading, and reverberant balance, layered together so convincingly that your brain, which has never had any reason to doubt its own ears, simply accepts the space it's been told exists. That question of illusion, of how a flat pair of speakers or a thin pair of headphones can trick a three-dimensional sense of hearing so thoroughly, is worth sitting with a little longer, and it leads us naturally toward the curious, carefully engineered world of stereo and surround sound, and how recordings first learned to fool us on purpose.
Let's set that world of stereo and surround sound aside for a moment, because before we get to how recordings fool the ear on purpose, it helps to understand how thoroughly the ear can be fooled by accident, or rather, how thoroughly the brain is willing to fill in gaps that were never actually filled in with sound at all. This is the territory of psychoacoustics, the study of how sound as a physical event and sound as a lived experience diverge from each other, sometimes in small ways and sometimes in ways so large they feel like magic tricks performed by your own skull. Start with something you have almost certainly experienced without naming it: masking. Imagine you're at a noisy dinner and someone across the table is telling a story, and just as they reach an important word, someone drops a fork. You don't hear silence where that word was. You don't hear the clatter and the word both, competing for space. Very often you simply don't hear the word at all, and yet, strangely, you don't notice its absence either. Your brain, drawing on the shape of the sentence, the rhythm of the speaker's voice, the context of what came before, quietly fills the gap with something plausible, and you walk away certain you heard the whole sentence. This phenomenon has a formal name: the continuity illusion, or sometimes phonemic restoration, and it was studied carefully in the 1970s by the psychologist Richard Warren, who ran an experiment that still holds up as one of the cleanest demonstrations in all of hearing science. Warren took a recorded sentence, cut out a specific speech sound, a phoneme, and replaced that exact gap with a burst of noise, a cough-like sound, nothing subtle. Listeners played the sentence, reported hearing the missing sound perfectly clearly, sitting right there inside the noise, and most of them could not even say with confidence which part of the sentence the noise had occupied. Their brains had done something remarkable. They hadn't just guessed the missing sound. They had synthesized the actual sensory experience of hearing it, layered underneath the interrupting noise, as though the noise were simply passing behind the word, rather than replacing it. This is worth pausing on, because it tells you something important about what hearing actually is. It is not a passive recording process, a microphone dutifully capturing whatever air pressure changes happen to arrive at your eardrum. It is an active, predictive, story-building process, constantly comparing incoming sound against expectations built from a lifetime of language, music, and everyday acoustic experience, and filling in whatever seems most probable when the raw evidence runs short. Masking, in its broadest sense, is simply what happens when one sound makes another harder or impossible to detect, and it isn't limited to loud sounds swallowing quiet ones in the same instant. There's also a gentler, stranger version called temporal masking, where a loud sound can mask a soft one that comes shortly before it even starts, a kind of masking that reaches slightly backward in time, called backward masking, as well as one that lingers forward for a short stretch afterward, called forward masking. Backward masking sounds almost like it violates cause and effect, but the explanation is fairly mundane once you know that your auditory system takes a small amount of time, measured in milliseconds, to fully process and register a sound. If a much louder sound arrives while that processing is still underway, it can overwhelm and erase the trace of the quieter one that technically arrived first, the way a fresh coat of wet paint can still swallow a thin pencil mark laid down moments earlier if you go over it quickly enough. From masking, it's a short step to another quietly astonishing psychoacoustic phenomenon, the missing fundamental. Picture a low musical note, say a note whose fundamental frequency sits around 100 Hz. That fundamental is normally the strongest, lowest component of the tone, the one that most defines its pitch, with a series of quieter overtones stacked above it at multiples of that frequency, 200 Hz, 300 Hz, and so on. Now suppose you play that same note through a small speaker, physically incapable of reproducing anything as low as 100 Hz, the way old telephone lines or small radios historically could not, so that only the higher overtones actually reach your ear. You would expect to hear a thin, oddly pitched sound missing its foundation, and yet listeners overwhelmingly report hearing the original low pitch anyway, as clearly as if the fundamental were physically present in the air. Your auditory system, presented with a family of evenly spaced overtones, infers the fundamental that would have produced them and reconstructs its pitch internally, essentially doing a piece of mental arithmetic and trusting the answer completely. This is precisely why old telephones, physically unable to transmit very low frequencies, never made men's voices sound like they were missing their bass entirely, and it's part of why small computer speakers and tiny earbuds can still convey a passable sense of a booming bass line, even though the actual low-frequency energy involved may be far weaker than what your ears report experiencing. Related to this, though distinct from it, is the phenomenon of combination tones, first documented in the 18th century by the Italian violinist and composer Giuseppe Tartini, who noticed that when he played two notes together, cleanly in tune on the violin, a third, quieter tone would sometimes seem to emerge from nowhere, a phantom pitch related mathematically to the two real ones, typically equal to the difference between their two frequencies. Tartini called it the terzo suono,
the third sound, and for a long time, musicians treated it almost as folklore, a private trick of well-tuned intervals. We now understand it as an artifact of how the ear itself processes sound, since the inner ear does not behave as a perfectly linear system, one where output scales cleanly and predictably with input. Instead, especially at higher volumes, it introduces small distortions, and those distortions generate genuinely new frequencies that weren't present in the original air pressure waves at all, frequencies produced by your own biology rather than by the instrument. In other words, a phantom sound that Tartini's students could reliably tune their playing against was not, technically, in the room. It was partly inside their own cochleas, manufactured on the spot by the mechanics of hearing itself. All of this points toward a broader and rather comforting truth about the ear, which is that it is not a fragile, static instrument constantly straining to keep up with the world, but an adaptive one, quietly recalibrating itself to whatever conditions it finds itself in. Step into a quiet room, and your hearing sensitivity gradually sharpens over the following minutes, a process called auditory adaptation, as the nervous system, no longer needing to guard against loud incoming sound, gently turns up its own internal gain to catch fainter and fainter detail.
This is part of why a bedroom that felt reasonably quiet when you first lay down can seem, 20 minutes later, filled with small sounds you swear weren't there before. A clock, a distant pipe, the hum of a refrigerator 2 rooms away. Nothing changed in the room. Your ears simply adjusted their sensitivity to match the new, quieter baseline, the same way your eyes slowly adjust to darkness and start recovering detail in a room that initially seemed pitch black. And this adaptive, almost storytelling quality of hearing shows up again in a phenomenon closely related to the continuity illusion but slightly different from it, called auditory streaming, or sometimes phantom continuity in the specific case of tones. If you play a steady tone, then briefly interrupt it with noise, then resume the tone at the same pitch and level, listeners typically report hearing one continuous, unbroken tone running straight through the noise, rather than 2 separate tones with a gap in between. Your brain, having already established the pattern of a sustained tone, treats the noise burst as an intrusion happening in front of that tone rather than evidence that the tone stopped, and it reconstructs the missing piece rather than reporting an interruption. It is the same underlying principle as Warren's restored phoneme, generalized beyond speech to something as simple as a single sustained pitch, and it suggests that this kind of perceptual bridging isn't a special trick reserved for language. It seems to be a basic operating principle of hearing itself, the mind's quiet insistence on continuity even when the evidence arriving at the ear is genuinely broken. Which raises a natural question, one worth carrying gently into the next stretch of this journey. If hearing is this willing to construct a stable, continuous world out of scattered and incomplete evidence, what happens when the brain has almost no reliable evidence to work with at all, in the near silence of a very quiet room, or in the strange, self-generated hush of total sensory deprivation? Let's set that question aside for a moment, not because it isn't worth answering, but because it points toward something else first, something about how the brain doesn't just fill in gaps in sound, it also builds entire structures out of sound, structures we call speech and music. And understanding how that construction happens will make the deprivation question easier to sit with later. Start with speech, because speech is, acoustically, a mess. If you looked at a spectrogram of someone talking, a visual plot of frequency against time, you would not see anything resembling the neat, discrete letters of an alphabet. You would see a smeared, continuous river of sound, formants sliding into each other, consonants bleeding into vowels, with no clean boundary marking where one phoneme ends and the next begins. This is called the segmentation problem, and it puzzled early speech scientists for decades. When you read a printed sentence, there are little gaps of white space between the words. Spoken sentences have almost none of that. The pauses you think you hear between words are, for the most part, not in the acoustic signal at all. They are inserted by your brain, after the fact, based on your knowledge of where words are supposed to begin and end. This is easiest to notice when you listen to a language you do not speak. It often sounds like a fast, unbroken stream because you lack the internal dictionary needed to carve it into pieces. A fluent speaker of that same language hears the identical acoustic signal and experiences it as a series of distinct, separable words, spaced out almost as clearly as if someone had printed them on a page. The sound reaching both listeners' ears is the same. The experience is entirely different, and the difference lives in stored knowledge, not in the air. Infants solve this problem remarkably early, and the way they solve it offers a small window into how flexible the auditory system is before it settles into the habits of a single native language. Newborns can, in laboratory settings, discriminate between the rhythmic patterns of languages they've never heard, and within their first year, they begin narrowing that broad sensitivity down to the specific sound contrasts that matter in the language spoken around them. This is part of why certain distinctions that are crucial in one language, like the difference between an R and an L sound in English, can become genuinely difficult for adult speakers of languages that don't make that distinction, even though as infants they were perfectly capable of hearing it. The ear does not lose the raw sensory capacity so much as the brain stops bothering to sort along that particular dimension, because it has learned that dimension isn't useful for the language it needs. Perception, in other words, is pruned by experience, the same way a path through a garden gets clearer the more it is walked and the less used paths grow over. Music asks a related but distinct question of the auditory system, because unlike ordinary environmental sound, music is built, quite deliberately, out of pitch relationships that repeat and pattern that anticipates itself. And one of the most basic organizing forces in music is rhythm, the sense of a pulse you can tap your foot to even when no one is telling you to. Rhythm has a peculiar hold on attention, one that researchers describe using a concept called entrainment, borrowed originally from physics, where it referred to the way two swinging pendulums placed near each other on a shared surface will, over time, gradually synchronize their swings because of tiny vibrations passed between them. Something loosely analogous seems to happen between a regular beat and the rhythms of attention in the brain. When you listen to a steady pulse, neural activity appears to align itself with the timing of that pulse, so that moments of heightened perceptual sensitivity cluster right around where the next beat is expected to fall. This is part of why a well-timed rhythm can make it easier to predict and even physically move with a piece of music, and it may be part of why humans, almost uniquely among primates, find it natural to synchronize movement to an external beat, tapping,
swaying, dancing, drumming, in ways that most other animals do not spontaneously do. Layered on top of rhythm is the question of pitch relationships, and this is where the story of music slides into some genuinely tangled territory, because it sits at the boundary between the physics of sound and the learned habits of a listening brain.
Consider two notes played together. Some combinations sound restful, stable, what musicians call consonant. Others sound tense, unresolved, what musicians call dissonant. For a long time it was tempting to explain this purely through physics. When two notes have frequencies that form simple ratios, like an octave, which is a 2-to-1 ratio, or a perfect fifth, which is close to 3-to-2, their overtones tend to line up neatly, producing a smooth, blended sound. When the ratio is more complex, the overtones clash slightly out of alignment, producing a rougher, beating quality that the ear tends to interpret as tension. This is a real acoustic phenomenon, and it does explain part of why certain intervals tend to sound consonant across many different cultures and historical periods. But it does not explain everything, and this is worth sitting with slowly, because it is one of the places where sound science is honestly still unsettled. What counts as pleasantly consonant versus interestingly dissonant has shifted across musical history in ways that pure physics alone struggles to account for. Intervals that sounded jarring and forbidden to listeners in medieval Europe, certain combinations were once genuinely called the devil in music, came to sound ordinary and even pleasant to later generations raised on different harmonic conventions. And listeners from musical traditions built on entirely different tuning systems. Some music around the world uses scales with intervals that don't map neatly onto the ratios common in Western harmony, can find Western consonance and dissonance judgments genuinely puzzling, or hear tension and resolution in places a Western-trained ear would not expect. This suggests that while the raw acoustic roughness of clashing overtones sets some baseline, a great deal of what we experience as musical pleasantness is layered on top through exposure, through the sheer accumulated hours of hearing certain patterns resolve in certain ways within a particular musical culture. Your ear is, in this sense, doing something similar to what it does with speech. It has quietly memorized the grammar of the music you grew up hearing, and it uses that memorized grammar to decide, moment to moment, what feels settled and what feels like it wants to move somewhere else. This blending of raw physics and personal history becomes even more apparent once memory and emotion enter the picture, because at that point, hearing stops being simply a matter of accurate detection altogether. A song heard during a particular season of someone's life can become permanently linked, in memory, to the emotional tone of that period, so that hearing it decades later doesn't just recall the tune, it can bring back a rush of feeling that seems to arrive before conscious thought catches up, a kind of instant emotional weather system triggered by a few opening notes. Researchers studying this have found that musical memories tend to be unusually resistant to the kind of fading that affects other autobiographical memories, and that emotionally significant music seems to draw on some of the same neural circuitry involved in reward and memory consolidation more broadly, though exactly how tightly that circuitry links sound, memory, and feeling together is still an area of active study rather than a fully settled map. What is clear is that by the time a listener consciously registers a sound as beautiful, or nostalgic, or unsettling, an enormous amount of quiet, fast, mostly invisible processing has already happened, sorting the raw pressure waves into rhythm, into pitch relationships, into learned grammar,
into memory, long before that finished feeling-laden experience ever reaches awareness.
And once you accept that so much of hearing is built rather than simply received, it becomes worth asking what happens at the edges of that process, in the moments when the incoming sound nearly disappears altogether, and the brain is left with barely any raw material to build from at all. Let's stay with that question for a while, because the edges of hearing turn out to be a strange and revealing place, and one of the strangest things about them is that true silence is almost never what people expect it to be. Start with an ordinary room, the kind most people spend their evenings in. It feels quiet. The television is off. The street outside has gone still. Maybe someone has already fallen asleep nearby. But an ordinary quiet room is, acoustically speaking, a very busy place. Sound waves leaving a source, a furnace fan, a distant car, a voice from another room, don't simply travel to your ear and stop. They bounce. They strike walls, ceilings, furniture, glass, and each surface sends part of that energy back into the room at a slightly different angle, a slightly different moment. What you hear is not one sound, but a rapid, overlapping cascade of the same sound arriving from many directions in quick succession, and it's this cascade, more than the original sound itself, that gives a room its particular acoustic personality. A bathroom sounds bright and lively because tile and porcelain reflect sound almost completely, sending it bouncing many times before it fades. A room full of thick carpet, heavy curtains, and upholstered furniture sounds hushed and close because soft, fibrous materials absorb much of that energy on contact, converting the tiny mechanical vibrations of sound into an even tinier, imperceptible amount of heat, rather than reflecting them back into the air. This tale of reflected sound has a name: reverberation, and it can be measured with a surprising amount of precision. Acousticians often describe a room by how long it takes for a sound to decay by 60 decibels after the source stops, a figure usually just over a second in a comfortable living room, closer to 2 or 3 seconds in a tiled stairwell, and, in certain cavernous stone cathedrals, stretching out to 8 or even 10 seconds, so that a single struck note can still be gently dissolving in the air long after the choir has moved on to the next phrase. Stretching out to 8 or even 10 seconds, reverberation, and it can be measured with a surprising amount of precision. Stretching out to 8 or even 10 seconds, so that a single struck note can still be gently dissolving in the tails tezer, or even tenors, in the naish, and any sons, in the seis, heavy zer, face. Stretching. Medieval composers, working in exactly those cathedrals, seem to have understood this intuitively, even without the vocabulary to measure it. Music written for long, reverberant stone spaces tends to move slowly, favoring sustained chords and gradual harmonic shifts, because fast, busy musical lines simply smear together into an indistinct wash when each note lingers for several seconds after being sung. Move the same fast, intricate line into a small wood-paneled chamber where reverberation might last only a few tenths of a second, and suddenly the details snap into focus. The room, in a very real sense, edits the music before it ever reaches the ear, and composers across history have written with that editing in mind, whether or not they thought about it in those terms.
Recording studios and concert halls take this reasoning and turn it into deliberate design. A vocal booth is built to be acoustically dead, its walls lined with foam wedges or fiberglass panels shaped specifically to trap sound waves and prevent them from bouncing back, so that a recorded voice arrives at the microphone clean, without the smearing tail of a reflective room attached to it. A concert hall does something almost the opposite, shaping its walls and ceiling with the intention of producing exactly the right amount and timing of reflection, enough to make the sound feel warm, full, and enveloping, but not so much that a rapid orchestral passage collapses into mush. Getting this balance right is notoriously difficult. Several famous concert halls have needed significant acoustic renovations years after opening, not because anything was structurally wrong, but because the reflected sound behaved in ways that didn't match what the architects and acousticians had predicted on paper. A reminder that even with all of modern physics available, room acoustics still holds a few stubborn surprises. There's a particular kind of room, though, that pushes this idea of controlling reflection to its logical extreme, and it belongs less to the world of music than to the world of engineering, and, occasionally, to the world of unsettling internet curiosities. An anechoic chamber is a room designed to reflect essentially no sound at all. Its walls, floor, and ceiling are covered in deep foam wedges, sometimes suspended, so that even the floor itself doesn't offer a hard reflective surface, and the effect is to absorb sound so thoroughly that almost nothing bounces back.
Engineers use these rooms to test how loudspeakers, microphones, or even the whirring components of new appliances actually sound, without a room's own acoustic signature interfering with the measurement. One chamber, built by an audio company in Minnesota, holds the distinction of being verified as the quietest place on Earth, with a background sound level so low it's measured in negative decibels, a figure that sounds like a physics error until you remember that the decibel scale is simply a comparison against a reference point, and it's entirely possible to fall below that reference. People who have spent time inside such a chamber tend to describe the experience the same way, and it isn't peaceful. Without any reflected sound to fill in the space, the silence feels less like an absence and more like a pressure, something you can almost feel against your ears. And within a short time, usually just a few minutes, most visitors start noticing sounds they'd never consciously heard before, because those sounds were always there, just permanently masked by the ordinary noise of daily life. The rush of blood moving past the inner ear becomes audible as a soft, steady whoosh. The mechanical action of breathing, air passing through the nasal passages, becomes a distinct, textured sound rather than a silent background process. Some people even report hearing a faint, high ringing that seems to have no external source at all, which is very likely their own auditory system, deprived of any incoming signal to process, beginning to generate a kind of internal static, not unlike the way closed eyes in a pitch-dark room can still produce faint drifting patterns of light. The visitor record for staying inside that particular Minnesota chamber alone, in the dark, is often cited as under an hour, and most people find it considerably less comfortable than that number might suggest. This is worth pausing on, because it reveals something important about the nature of quiet itself, something that matters well beyond the walls of a specialized testing chamber. The human auditory system did not evolve to sit idle. It evolved to constantly monitor an environment that was,
for nearly all of human history, never completely silent, full of wind, insects, distant animals, the small sounds of other people nearby. A total absence of external sound is, in a sense, an unfamiliar and slightly artificial situation for the ear to be in, and the nervous system responds to that novelty by turning its attention toward whatever signal remains, even if that signal is nothing louder than a pulse or a breath. This is part of why people who move into an extremely quiet bedroom, perhaps after soundproofing a room or installing very effective double-glazed windows, sometimes report that the silence itself feels distracting at first, or that they become oddly aware of a faint ringing or their own heartbeat as they try to fall asleep, a phenomenon that usually settles down within a few nights as the nervous system adjusts its expectations and stops treating the new quiet as something requiring extra vigilance. Modern noise-canceling headphones work with a related but distinct idea, and it's worth understanding briefly, because the trick involved is genuinely elegant. Rather than absorbing sound the way foam does, active noise cancellation uses a tiny microphone to listen to the incoming noise, then generates a new sound wave that is, as closely as the electronics can manage, the exact mirror image of that noise, peaks where the original had troughs and troughs where it had peaks. When the two waves meet, they interfere with each other in a way that largely cancels them out, which is why the technology tends to work especially well against low, steady sounds, like an airplane engine's hum, where the waveform is simple and predictable enough to mirror accurately, and works far less well against sudden sharp sounds like a cough or a drop tray, where there simply isn't enough time to build and deploy the canceling wave before the sound has already passed.
And so silence, it turns out, is rarely a single clean condition. It exists on a spectrum, shaped by walls and reflections, by the deliberate absorption of a recording booth, by the extreme engineered emptiness of a chamber built specifically to have almost nothing left to hear, and by the ear's own tendency to fill any remaining gap with whatever faint signal it can still find. Which raises a related and equally interesting question. What happens when there is sound, plenty of it, but it's sound the brain has decided not to bother listening to at all? Human hearing, for all its sensitivity, only covers a narrow slice of what sound actually is. Most people can hear frequencies roughly between 20 Hz and 20,000 Hz, and that upper limit tends to shrink with age, quietly, without much notice, until someone in their 40s realizes they can no longer hear the faint whine some televisions and older fluorescent lights give off, a sound a child in the same room hears easily. But sound itself doesn't stop at either edge of that range. It simply keeps going, into territory human ears were never built to register, and that territory turns out to be busy, strange, and in some cases, enormous in scale. Below 20 Hz lies the infrasonic world, sound so low in pitch that it stops feeling like a tone and starts feeling like a pressure, a pulse, sometimes even a mood, in a room without an obvious source. Elephants use this range constantly. They produce deep rumbling calls, some well below the threshold of human hearing, that travel for several kilometers across open savanna, allowing separated herds to stay in loose contact across distances that would otherwise mean total silence between them. Researchers studying this only pieced it together properly in the 1980s, when a bioacoustician named Katie Payne, who had earlier done similar work with whale song, noticed a faint throbbing sensation in the air near elephants at a zoo, something she could feel more than hear, and suspected correctly that there was sound happening below her own hearing range. Elephants seem to receive some of these low calls partly through the ground as well as through the air, with sensitive tissue in their feet and trunk, picking up vibration that has traveled through soil, which is a genuinely different channel for sound than the one human ears rely on. Whales work in an even more dramatic version of this same idea, and part of what makes their calls carry so far involves the way sound behaves specifically in seawater, because the ocean isn't uniformly the same everywhere for sound to travel through. Water temperature and pressure change with depth in ways that bend sound waves, and at a certain depth in most oceans, usually somewhere around 600 to 1200 meters down, those two effects roughly cancel out to create a layer where sound travels at its slowest speed for that stretch of ocean. Because sound waves bend toward regions where they travel more slowly, this layer acts almost like a acoustic waveguide, trapping sound within it and letting it travel enormous distances with very little loss, sometimes thousands of kilometers, bouncing gently within this channel the way a whispered voice can carry unexpectedly far down a long, narrow hallway. Some large whales appear to call at frequencies and depths that take advantage of this channel, effectively broadcasting into a natural amplification system built into the ocean itself, though exactly how deliberately they exploit it is still an area researchers continue to study rather than something fully settled. Infrasound also shows up in contexts that have nothing to do with animals communicating on purpose. Large storms generate it, so do earthquakes, volcanic eruptions, and, notably, thunder. The crack of nearby thunder sits comfortably within the audible range and can be startlingly sharp, but the deep, prolonged rumble that follows a distant strike is partly a matter of that same sound traveling a longer, more complicated path, refracting through layers of air at different temperatures, echoing off clouds, hills, and the ground, smearing what began as a single sharp crack into something rolling and low. Much of that low rolling energy dips down toward and sometimes below the edge of audible hearing, which is part of why distant thunder can feel like it's registering somewhere in the chest as much as in the ears. Large meteor impacts and nuclear tests produce infrasound so powerful it can circle the entire planet, detectable by sensitive instruments days after the original event, still faintly rippling through the atmosphere. At the other end of the spectrum, above 20,000 hertz, lies the ultrasonic world, and this is where bats live, quite literally, since their entire hunting strategy depends on producing sound far higher than any human could ever hear, and then listening for the returning echo. A bat in flight emits rapid pulses, sometimes well above 100,000 hertz for some species, and then interprets the returning echoes with extraordinary precision, extracting not just the presence of an object, but its distance, its size, its texture, and whether it happens to be a moth in erratic evasive flight rather than a leaf drifting in the wind. This is echolocation, and what makes it especially impressive is the timing involved. Because sound travels at a fixed and fairly slow speed compared to light, a bat closing in on prey has to constantly recalculate distance based on how long each echo takes to return, adjusting its calls to be shorter and more frequent as it approaches, almost like tightening the beat of a metronome the closer it gets, so that its picture of the world updates faster the more urgently it needs that information. Dolphins and toothed whales use a related system underwater, generating clicks through structures in their heads and reading the echoes with a fatty organ near the jaw that helps channel sound back toward the inner ear, effectively hearing partly through their jawbone rather than through an ear canal the way humans do, since sound moves differently and generally more efficiently through water and through bone than through air. It's a reminder that hearing, biologically speaking, isn't tied to any one particular anatomical shape. It's tied to whatever structure happens to be good at picking up mechanical vibration and turning it into a nerve signal, and evolution has arrived at that solution more than once, in more than one shape, in more than one medium. Plenty of ordinary animals live comfortably in ultrasonic territory without anyone thinking of them as exotic. Domestic cats can hear well above 60,000 hertz, likely an adaptation for detecting the high, thin calls of rodents. And dogs, though less extreme than cats, still hear meaningfully higher than humans do, which is the entire principle behind a so-called silent dog whistle, which isn't silent at all, just pitched above the range where a human ear can register it while remaining perfectly audible, even piercing, to a dog nearby. Mice and rats communicate with each other partly through ultrasonic calls too high for humans to hear casually, including surprisingly complex vocalizations that some researchers have described as resembling simple song structures, discovered mostly because sensitive recording equipment happened to be listening in a frequency range no earlier scientist had bothered to check. Earthquakes bring both ends of this story together in an unexpectedly direct way. The shaking itself is, at its core, a very low-frequency vibration moving through solid rock, mostly well below what a human ear can register as pitch, which is why an earthquake tends to be felt as a lurch or a shudder rather than heard as a tone, at least until it's strong enough to rattle windows or shake objects that themselves begin producing audible sound as a secondary effect. Seismologists, studying these waves, use instruments built specifically to register vibration frequencies the human ear was never meant to process, translating ground motion into readable patterns the same way a thermometer translates heat into a number a person can actually use. Put all of this together, and the range of sound humans can hear starts to look less like the whole of sound and more like a narrow window cut into a much larger wall, useful for exactly the frequencies that mattered most to a mammal trying to hear footsteps, voices, and rustling leaves across roughly the distances early humans needed to survive. Everything above and below that window is still there, still happening, all the time, all around, carried through rock and water and air by creatures and forces that never needed permission from a human ear to make themselves heard. Which leads naturally to a related question worth sitting with for a moment. Whether hearing that narrow window at all is really a passive event, or whether the brain, in its usual quiet way, is doing something far more active with that sound than most people ever notice. Before any of that brain question can be answered, though, it helps to follow sound somewhere else entirely, into machines built by people who wanted to capture it, move it, store it, and eventually manufacture it from nothing at all. A microphone, at its heart, is a strange kind of translator. It takes something the air is doing and turns it into something a wire can carry. The earliest working versions, built in the late 1800s alongside the telephone, used a thin diaphragm that vibrated in response to sound pressure, pressing against a small chamber of carbon granules whose electrical resistance changed as they were squeezed and released. That changing resistance became a changing electrical current, and that current, sent down a wire, could be turned back into vibration somewhere else. It was a clumsy, hissy, limited technology by later standards, but it proved something important, that the physical motion of sound could be converted into an electrical signal, carried a great distance, and converted back, all within a fraction of a second, faster than the sound itself could have traveled through open air to reach the same destination. Modern microphones work on a few different principles, but the most common type found in everyday devices, the condenser microphone, still relies on the same basic idea of a diaphragm moving in response to pressure changes, this time paired with an electrically charged plate positioned just behind it. As the diaphragm flexes inward and outward with each compression and rarefaction of the sound wave, the distance between it and that fixed plate changes ever so slightly, and that tiny shift in distance changes the electrical capacitance between them, producing a fluctuating voltage that mirrors the shape of the original sound wave with remarkable fidelity. The diaphragm itself is often thinner than a human hair, light enough to respond to pressure changes measured in billionths of an atmosphere, which is part of why a good microphone can pick up a whisper across a quiet room or the faint hiss of breath before a word is even spoken. A speaker does the whole process in reverse, and it's worth noticing how elegant that reversal is. Send an electrical signal into a coil of wire wrapped around a magnet, and the coil moves in response to the fluctuating current, pushing and pulling a cone of paper or plastic attached to it. That cone shoves air molecules forward and pulls them back, compressing and rarefying the air in a pattern that matches the original electrical signal, which itself was shaped to match the pattern of the original sound. 3 separate physical systems, air pressure, electrical current, and mechanical motion, are made to mirror one another closely enough that a listener across the room can't easily tell the difference between a recorded voice and a live one, even though what's reaching their ear has been translated twice and passed through at least 2 entirely different kinds of physics along the way. For most of the 20th century, all of this translation happened in an unbroken, continuous way, which is what people mean when they talk about analog recording. A phonograph needle cut a groove into a soft wax or vinyl surface, and the shape of that groove, its tiny wiggles and curves, was a direct physical trace of the sound wave that produced it, the same way a river carves a shape into a landscape that reflects, however imperfectly, the water that shaped it. Magnetic tape worked on a related principle, arranging microscopic magnetic particles into patterns that varied continuously in strength, again tracking the original sound wave without ever breaking it into separate pieces. The appeal of analog recording, and the reason some people still prefer it today, is exactly that continuity. Nothing is measured at intervals and rounded off. The physical medium simply follows the wave, the way a hand follows the curve of a banister down a staircase, capturing every small transition rather than jumping from step to step. Digital recording, which took over gradually from the 1980s onward, works on an entirely different premise, and understanding it clears up a great deal of confusion about what a modern recording actually contains. Instead of tracing the wave continuously, a digital recorder measures the air pressure, or more precisely, the electrical voltage representing that pressure, at an extremely rapid series of individual moments, then stores each of those measurements as a number. A standard compact disc, for instance, takes over 44,000 of these measurements every single second, each one capturing the wave's exact height at that instant and rounding it to the nearest of over 65,000 possible values. Play those numbers back quickly enough, smoothing the tiny gaps between them, and the ear reconstructs something that sounds, for nearly all practical purposes, identical to a continuous wave. The same way a film reel of still photographs shown quickly enough
creates the smooth illusion of motion, even though nothing in the reel itself is actually moving. That sampling rate, 44,000 times a second, isn't an arbitrary number. It connects directly back to something covered earlier about the upper edge of human hearing, sitting somewhere around 20,000 Hz for a young, healthy ear. A foundational insight in this kind of engineering worked out mathematically well before digital audio existed as a consumer product, showed that to accurately capture a wave of a given frequency, a system needs to sample it at a rate at least twice that frequency. Sample any slower, and the reconstruction doesn't simply lose detail, it can actively produce false frequencies that were never present in the original sound at all, a strange kind of digital mishearing baked directly into the mathematics. Choosing a sampling rate a little above 40,000 times a second, then, wasn't guesswork. It was a deliberate decision to comfortably cover the entire range of frequencies a human being could ever plausibly hear, with a small margin left over. Compression adds another layer to this story, and it's one that quietly shapes how most people listen to music and speech today, whether they think about it or not. An uncompressed digital recording captures an enormous amount of information, far more, it turns out, than most human ears can consciously use. Compression formats, built for everyday listening, exploit that gap, using what's understood about the limits and quirks of human hearing to discard the parts of a signal least likely to be missed. A loud sound, occurring at the same moment as a much quieter one, for example, tends to mask that quieter sound almost completely, making it functionally inaudible even though it's still technically present in the air. A well-designed compression algorithm can identify moments like that and simply not bother storing that masked information, shrinking a file dramatically while leaving the actual listening experience nearly untouched for most people, most of the time. It's less like deleting parts of a photograph and more like a skilled editor removing sentences from a paragraph that nobody was going to reread anyway.
Outside of recorded music and speech, this same underlying idea, using sound to detect and image things a person can't see directly, does quietly serious work in the physical and medical world. Sonar, developed and refined significantly during wartime efforts to detect submarines, sends a pulse of sound into water and listens for its echo, calculating distance from the simple, reliable fact that sound moves through water at a known, roughly consistent speed. Time the echo carefully enough, and a hidden shape in dark water becomes a rough outline on a screen, the same basic principle used by a bat navigating a cave, just built from wires and transducers instead of a mammalian nervous system. Medical ultrasound imaging works on a closely related idea, though tuned to a very different scale. A handheld device presses gently against skin and sends extremely high-frequency sound, well above what any human ear could register, into the body, then listens for the pattern of echoes bouncing back from the different tissues underneath. Muscle, fluid, bone, and organ tissue all reflect sound differently, and a machine built to interpret those subtle differences in echo timing and intensity can assemble them into a live, moving image, which is how a technician can watch a heart valve open and close, or parents can first see the outline of a child still developing in the womb, all built entirely out of sound too high for anyone in the room to hear passing quietly through the body and back out again. And yet for all of this remarkable translation, from wax cylinder to compressed audio file to a screen built from echoes, something worth sitting with quietly for a moment is that no recording, no matter how advanced,
actually reconstructs the original event itself. It reconstructs a very good approximation of the air pressure changes that event produced, filtered through a chain of physical and mathematical choices, each one reasonable, each one slightly lossy, stacked one on top of another. The gap between an event and its recording, small as it usually feels, never fully closes, which raises a quieter and more personal question about what happens on the other end of all this technology, inside the listener's own head, where the final translation of sound into experience actually takes place.
There is an old question, older than any microphone, that tends to surface around this point in the night, usually in the form of a tree falling in an empty forest. If no one is there to hear it, does it make a sound? The honest answer depends entirely on what a person means by the word, and untangling that is a gentle way to close out everything this narration has walked through so far. If sound means a physical event, a pattern of pressure moving outward through air in expanding waves, then yes, the tree makes a sound whether or not anyone is present. The physics does not care about listeners. Wood fibers tear, branches whip through air, the trunk strikes the ground, and molecules get shoved into motion in every direction, spreading outward exactly as they would if a forest ranger happened to be standing there with a notebook. Instruments left in the empty forest, a simple pressure sensor and a recorder, would register the event without hesitation, the same way they register wind or rain or the distant complaint of a truck engine on a highway a mile off. In this sense, the question resolves quickly, and the forest keeps no secrets from a machine. But if sound means the experience of hearing, the felt quality of a low booming crash, then the answer changes completely, because that experience has never been shown to exist anywhere except inside a nervous system built to produce it. Without an eardrum to catch the pressure wave, without tiny bones to amplify it, without hair cells to convert it into electrical signaling, without an auditory cortex to organize that signaling into something recognizable as a sound, there is no hearing taking place at all. There is only air moving the way air moves when disturbed, indifferent, mechanical, silent in the deepest sense of the word. The falling tree, heard by no one, produces a wave and nothing more. The sound, meaning the experience, requires a listener to complete it. This is not really a trick of language, so much as a genuine seam in how the world is built, the seam between what physics can fully describe and what physics has never been able to explain, which is why the wave and the hearing of it deserve to be thought of as two different things joined by biology, rather than as the same thing wearing two names. The wave is public. Any properly built instrument in the forest could detect it, and two separate instruments would agree closely on what they measured, because they are measuring something external and shared. The hearing is private in a way instruments cannot reach. No device has ever been built that measures the subjective quality of a sound the way a barometer measures pressure, because that quality does not seem to live in the physical signal at all. It lives somewhere downstream, in whatever it is that happens when a brain finishes processing the signal and a person becomes, however briefly, aware of having heard something. Consider a very ordinary version of this puzzle, one much smaller than a falling tree. Somewhere tonight, in some quiet room, untouched by any listener, a clock is ticking. The mechanism inside is doing exactly what it always does, a small spring releasing energy in measured pulses, a hammer or escapement tapping in a steady rhythm, the surrounding air receiving that rhythm as a real physical disturbance. If a microphone were placed nearby, it would register those pulses cleanly,
waveform after waveform, evenly spaced, entirely real. And yet there is no ticking happening in that room in the experiential sense, no small sound that anyone is having, because the specific texture of a tick, that crisp little percussive event a person recognizes instantly in memory, is not a property of the air. It is something a nervous system builds, and it only gets built when a nervous system happens to be present and paying attention.
This distinction between the wave as a physical fact and the experience as something else entirely connects to a puzzle that thinkers have circled for centuries without fully closing, sometimes called the hard problem of consciousness, though the phrase itself came much later than the puzzle. Physical descriptions of sound, however detailed, describe frequency, amplitude, timing, the physical structure of the cochlea, the firing pattern of neurons in the auditory cortex, and every one of those descriptions can in principle be made perfectly complete without ever once explaining why any of it is accompanied by an experience at all. It seems entirely possible to imagine, in a thought experiment sense, a system that processes sound exactly the way a human does, registers the same frequencies, produces the same neural firing patterns, even reports verbally that it heard something, and yet has no actual felt experience of hearing behind any of it, no inner listening happening at all. Whether such a system could really exist is deeply uncertain and probably unanswerable with current tools, but the fact that the question can even be coherently asked says something important. It says that hearing is not fully explained just by explaining the physics of vibration, and it is not fully explained just by explaining the biology of the ear either. Somewhere between the physical signal and the subjective moment of noticing it, something happens that science can trace the edges of without yet being able to say exactly what it is. None of this should feel unsettling so much as quietly humbling, a reminder that a person listening to rain against a window tonight is not simply receiving information the way a microphone receives it. Something is happening in that listening that goes beyond the transfer of pressure patterns from outside to inside, something that turns a physical event into a small private experience unlike anything a diagram of a sound wave could ever fully capture. The wave can be measured, graphed, reproduced, compressed into a file, and sent anywhere in the world in an instant. The experience of hearing it cannot be transferred at all. It can only be recreated, imperfectly, inside another nervous system willing to go through the same trouble of building it fresh. And there is a strange, quiet comfort tucked inside that limitation, because it means each act of listening is, in a small way, unrepeatable. The particular hush a person notices in a house at midnight, the particular warmth of a familiar voice heard through a phone from very far away, the particular hollow knock of a spoon set down on a wooden table in an otherwise silent kitchen, none of these can be copied exactly and handed to someone else. They can only be caused, again and again, by patterns of air moving into ears built to notice them, and each time a person notices, a bridge gets built, briefly, between something as impersonal as a pressure wave and something as personal as a memory being formed in real time. That bridge does not last. The pressure pattern dissipates within a second or two, dispersing into the general disorder of the room, and the neural activity that briefly organized it into an experience settles back down as well, leaving behind only whatever trace memory
chooses to keep. But for that short window, sound is one of the very few things that manages to connect the impersonal physical world directly to the personal inner one, connecting a vibration in matter to a feeling in a mind, connecting a person standing in one place to another person, or another moment standing somewhere else entirely, connecting distance to intimacy, and the present moment to something that will soon only exist as memory. That may be the quietest way to close out a very long walk through everything confusing and remarkable about sound, wax cylinders and cochlear implants, echolocating whales and speakers vibrating in dark rooms, unheard trees, and ultrasound scans watching hearts they cannot hear. Sound turns out to be temporary by nature, here and then gone, a pattern that borrows matter for just long enough to mean something before letting it go again. And maybe that impermanence is not a flaw in the story at all, but the entire reason any of it was worth listening to in the first place. The room is quiet now, or as quiet as any room ever truly gets, full of small vibrations settling, breath slowing, the last thoughts of the evening dispersing the way sound always does, gently, without insistence, into rest. Rest well.